My talk about attacking Android applications. My name is Dario incalza. One slide to introduce myself. I'm a mobile security expert at Science Security, where in my team we pen test mobile applications. So every company that has a mobile application, financial, healthcare, social media, everything you can think of, we pen test that. I also do some bug bounty hunting. I'm quite active in the open source community. I have a personal website here. And I tweet a lot on Twitter about stuff that keeps my mind going, mostly Android security or mobile security in general. The company I work for, Science Security, we do everything security related in web, mobile, IoT, and infrastructure. We do architectural reviews, we do source code reviews, we do pen testing, red teaming, blue teaming, everything you can think of with regards to security. We also offer secure software development, consultancy. We are based in Belgium, Botselaar. You might don't know that city. It's near Leuven, home of Stella Artois beer, if you know that one. And that's our company website. So what are we talking about today, or what I'm going to talk about today? How are Android apps structured? So a first real quick introduction to Android apps under the hood. Some attack surfaces that exist. So how are hackers thinking about attacking your app? Some things you might don't have to think about when you develop an app, but that will give you a clear view of what hackers, from the point of view of a hacker. Then we're going to attack applications statically. So that means without running the app, just looking at the source code, reverse engineering, and also looking at them dynamically. So when they're running on the device, what can you infer from that? What is the app storing? What is it using? Which network request is it making? And then some countermeasures also. We're not only hacking apps today, but we'll also, I'll give you some pointers on what you can do as a developer. So a quick introduction, probably know this. The Android platform stack, how does it look like? Well, you have your applications, you have your that interact with your Java API framework. They're built on top of native libraries and the Android runtime that is basically the sandbox around your app. Then you have your hardware abstraction layer, which basically makes sure that you, as a developer on a higher level, don't need to know how hardware works. You can just use the APIs that are there for you. And then you have the Linux kernel, which is basically becoming the Android kernel because there are some modifications. It's not pure Linux kernel. Android added its own specific modules. So an Android application is a .apk file. It's just a zip file. You upload it to the Play Store. You can sideload it on your app using ADB, of course. It can be dumped from the device. It's just a regular zip file, and it's always signed. So because it's a zip file, you can unzip it. And if you unzip it, these are the components that you'll see on a high level. You have your Android manifest file. You all know this. You have a resources index file. You have your classes.dex file, which contains the bytecode. So when your app is being compiled, you write it in Java source code or in any other language that compiles it to Java bytecode. And then it gets compiled to DEX bytecode, so Android bytecode. So that's the classes.dex file. And then when it's on your device, it will be compiled to native code on your device. In the past, Android did it while you were installing the app. So at installation time, now they have like an optimized scheme. They only compile parts of your app when the device is idle, and they optimize different parts when they find another spot in time. Then you have your resources, you have assets, and if you also include native libraries, you also have your native shared object files. And there goes my screen. Okay, let's try again. So this is what your APK looks like. Then you have your build process. Okay, this is not working. Can I use your laptop?
log you in first, so there's no compromising or otherwise shitty information on the screen. We need a USB stick with your slides. Bring an Apktool presentation. It's a toy.
Thanks for the technical intervention. I didn't catch your name, but
Mr. Hanna, I'm Hanna.
okay.
I'm speaking tomorrow, by the way, on Android things.
Okay. Well, the makeup is a little bit off here. So you have your.
It's not your fault. This is a problem because the IBM uses a different font rendering engine.
Ah, yeah, okay.
It's not his fault.
Thanks. So you have your build process. So you have your source code and your resource files on the left. You have your libraries that you're using on the right. They get sent through compilers. So you have your DEX compiler that transforms your Java source code. And then you also have your resources that are going to AAPT, which gives you the binary resources, which is just a binary representation. And that gives you the DEX files and your compiled resources in the final APK. And everything gets signed. So before you can upload it, you have to run the sign procedure. And so every file gets basically signed and added to the manifest, to a manifest file, which the Android runtime will check when you install the app. So a little bit on DEX bytecode before we go further. So DEX bytecode is the bytecode that gets executed on your device. So actually it gets compiled into native code in these new Android versions. It's register-based. Why is this important? Because you can also have stack-based, but with register-based you pass your values through registers and not on the stack. It's executed by, I'll probably have to update the slide, by the orde runtime, and gets compiled to native code on your device using DEX to ode, and it can be reversed to Java source code. Then you also have Smiley bytecode, which I'll be using in this presentation, which is a more high-level interpretation of the DEX bytecode, but it's still lower level than Java source code. And the reason why it's still possible to change Smiley bytecode and recompile the app, while if you go to Java source code, it just completely breaks because Java source code doesn't perfectly map on Android bytecode. This is an example. The contents of the method here is not important. It's just to show you how Smiley bytecode looks like. So when you reverse the bytecode, so you disassemble it basically from the Android app, this is the code that you get. And this is pretty readable for a human. Whereas you would see this in DEX bytecode, it's a little bit harder to read. And you can still see that you still have the notion of methods. You have your local parameters. You have operation codes that are still easy to understand. For example, a check cost, where you're checking if it's an integer. And then you have an invoke virtual, which will invoke the evaluate method on the int evaluator class. You pass something to your register here, the result to v0, and you return that object. So this is still pretty readable, and that's what I recommend when you look at an app, because you can patch code in here and it can still recompile. You have to re-sign it with your own certificate, but it's perfectly recompilable. While if you decompile it to Java source code, then it won't work. Even with no obfuscation, it's hard to get it back to work. So some attack surface. There are different attack models that you consider when you attack an app. So the first one is that they reverse engineer your app offline and online. So what that means is looking at the code like we did now. Or online means while your app is running, attaching a debugger, injecting code in its space, and basically tamper with the app while it's running. Then you have the attack model of an app that's on the device, but it doesn't have root access. So for example, you might be writing something sensitive to the SD card. Another app doesn't have root access, but it has the permission to read the SD card. Then you might leak some information there. So that's also an attack model you have to consider. And what if an app on the device gets root access because you have your rooted device and there's an app that says an ad blocker, for example, but you don't know what it does in the code, but you give it root access. What are the implications for your app that's running besides that app? A man in the middle, that means you don't touch the app, but you're just man-in-middling the app between, on network level between the app and the server to see what information is being sent over the wire. Or what the attack model of a person that has physical access to the device, that he can make a memory dump, for example, or if he can manipulate the app, what access does he have to the user's data? And then you translate it to some research questions. So how does the app handle authentication? For example, if it gets an access token, where does it store it? Where does it store credentials? If it's asking for credentials, where is it storing? How is it storing it? And does it use a proper session management? For example, if you log into your API and you get a token back, is the token being invalidated when the user logs out? How does the app store user data? Does it use cryptography? Where does it store it? Does it use API keys? How are those API keys? What can you do with those API keys and how are they protected in the app code? Are there maybe content providers that are exposed? Another research question is, how does the app communicate? Does it use HTTP? Does it use HTTPS? Or for financial apps, it's important that they do certificate pinning, for example. Is it doing that? Is it doing that properly? Because there has been a major issue with certificate pinning like a year ago discovered. And how does the app protect itself? So you have your secure architecture, but does it also use obfuscation, or does it use some dynamic checks while it's running? For example, it refuses to run on a rooted device, or it refuses to run on an emulator. How is that incorporated in the app? Does it do any checks in the first place? So in this part of the presentation, I'll show you some tools, how you can attack an Android app statically. So just a high-level overview. There's a little bit of overlap there. But you have your APK, you unzip it, then you have those SO libraries that I'll show you in one of my first slides. You have your classes.dex file and you have your resources. So if you start on top, you have your SO libraries, that's basic machine code. You can reverse engineer it using Radari or Hopper or ADAP Pro. And it gives you back an x86 RM or x86 64. Depends really on which native library you're decompiling, which version, which architecture. Then you have your classes.dex file, and then you have two options, or you do dex to jar, which I don't recommend, but a lot of people might want to see Java source code, but you'll also see that there are a lot of parts of your code that are not being decompiled because some decompilers simply can't decompile a given part of the code because it's too complex. Because they don't actually run the code, they symbolically evaluate the code, but sometimes these decompilers are not perfect, and it's really hard to get a good Java source decompiler. So what I always do is I go back to Bugsmiley, or I use Bugsmiley and Smiley to go back to Smiley bytecode, and from Smiley bytecode go back to Dex bytecode. And your resources, you can bring your resources back to an XML version using AAPT, which is just in your standard Android SDK. So there's no obfuscation there or whatever. It's just XML written into binary format, and when you want to reverse it, you just do the opposite with AAPT. An example on how you can use AAPT. So here I issued the AAPT-D, which stands for disassembled, and give me the XML tree of a file.apk on the Android manifest. And then this gives you the XML output. Now, it doesn't really look like XML, but this is according to the specifications of XML. So you have your elements, you have with ed, and how do you say that? The two dots. And then you have your attributes. You can see which permissions it uses and stuff like that. Even if an obfuscator is used that obfuscates resources, this will always work because this is the exact same thing that the Android runtime will also do, or they have a binary parser, but it's the same logic. And here, for example, it's maybe not readable, but you have your application element on top, and this gives you all the information about the application. Also, because it's popular, I added to this presentation is the APK tool. Who has played with APK tool? Yeah, it's a nice click and play tool from XDA developers. I originated on XDA developers. And it's a one-line command, and you have disassembled or decompiled the whole app. So, for example, if you do APK tool, command D, file.apk, it will disassemble the whole APK. It will reverse engineer it or disassemble it to smally bytecode. It will decompile your resources. But APK tool works fine if the app doesn't have any obfuscation or just small proguard obfuscation. But if a commercial obfuscator is being used, then APK tool might crash. That's why I like bytecode viewer. And bytecode viewer is a decompiler that is a collection of decompilers. So on this screen, you have 3 different decompilers next to each other. So let me check. Okay, in the middle, there's a bytecode decompiler, so that always works. That decompiler will never crash. It just reads out the bytecode. So it's obviously also in bytecode. And then on the left, you have in this specific example, the Procyon decompiler, and that's a really good Java decompiler, as far as you can have a really good Java decompiler. And it does a decent job at decompiling back to Java source code. And on the right, there's a Sunflower decompiler, which is also a different Java decompiler. But the cool part here is if one decompiler crashes, this is the same file, by the way. So if one decompiler crashes, you can jump to the bytecode for that part of the code, or you can jump to the Sunflower decompiler for that part of the code. So you always have different views on the code. And bytecode will always work, and the other 2 decompilers are there to give you the oversight. And you can just drop an APK and bytecode viewer, and it will decompile it. Then I made Droidgraph. This is one of my open source tools, and it's capable of finding structure in bytecode by giving you the classes and the interface relationship. So, for example, this is an open source APK, which is a 2048 game, and here you immediately see which class is extending an activity, for example. Or which is a comparator, which is an on-click listener, stuff like that. And even with obfuscation, it still gives you a good idea of how the relationship is in the code or how the code is structured, because the SDK calls like Android app activity will never be obfuscated, because then the Android runtime wouldn't know that it would need the activity clause of the Android SDK. So what would be obfuscated would be the main activity, but then we can still see that there's an obfuscated clause using or extending the activity clause, and that already gives you some insight. So this is, it's not really a complicated tool. It just makes a graph basically. But I needed it in some projects, and I decided to open source it. And it has an include and exclude function. So for this example, I excluded the whole support Android library because you have to, if you want to have backwards compatibility, you have to use that library, right? But it's overhead, so you can exclude that using a regex system. You can just write your own regex, and it will filter it from the graph. So we're attacking apps statically, and before we go further, just a quick lesson on cryptography. So you have basically 2 types of cryptography. You have symmetric cryptography, which is basically you have one key for encryption and decryption, which means that you have to find a way to share that secret. And examples of that are AES, Triple Desert Blowfish. And then you have public key cryptography, which is the second option of doing cryptography, which basically says you have a private and a public key, and the way you use these keys basically determine how what your use case is. So here are 2 use cases where you encrypt with your private key and you decrypt with your public key, and then you get a digital signature. And if you encrypt with your public key and you decrypt with your private key, then it means that you have confidentiality, because the private key will never leak, but you use the public key of somebody to send him a message, and you know that he guards his private key well, and he can only read the message. So that's important to know, because how are you distributing keys in your app, for example? And in this presentation I chose because I cannot go over every security assessment or every part of a security assessment. So I chose how can you find cryptography and how can you reason about cryptography in an Android app that you have to inspect or that you are developing. And the first thing you have to do is you have to locate where it is being used. So maybe you can see from the code names that might indicate which library is being used. Like, for example, is it just the Android SDK? Is it using Bouncy Castle? Is it using Spongy Castle? Is it using any other library? Does it use a hard-coded key? So that's another question you can ask yourself, because hard-coded keys are not advised in apps. Does it use a broken cryptography protocol? For example, is it using an MD5 hash to hash something that should use a better or stronger hash function because MD5 is deprecated? And then you also have RC4 or AES in EBC mode, and these are all weak versions of cryptographic protocols. And the last question, so okay, it is doing cryptography good, the app, but where does it store those keys? How does it handle those keys in the app? And that's also important. So an example here is, how do you locate cryptography? So I stick to the Android SDK, so if you want to do cryptography using the Android SDK, you'll probably use these classes. JavaX crypto.cipher, JavaX crypto spec, where you specify a key, and then you have a secret key object. And the strange notation here is basically in Smiley bytecode. So if you have a class, so the cipher class, translated to Smiley bytecode would be this. Now, at this point, we have disassembled the APK into Smiley bytecode. So, and you know that these classes look like this in Smiley bytecode. You can do a simple grep in your whole code base. So you grep recursively on this string and in your Smiley directory, which contains all your disassembled Smiley code. And that will basically give you all the files where this class is being used. And then it's up to you to inspect that code. And when I was doing a bug bounty, this is what I discovered. So this is an app. And when I did the grep, I got this, the lower rectangle. It brought me here because here a cipher class is being used. More specifically, you get an instance of that class. And then when I started inspecting that, I saw, okay, it's a cipher. A cipher is being used here. It needs some key. And then I looked upwards in the code, and there's a static part which defines a hard-coded cryptography key. So this app is encrypting something. So it's probably sensitive information. And it's doing the effort to encrypt it. But then the developer said, okay, I need to use an encryption key here somewhere. And it decided to code it statically. So there's a problem with this. Why? It didn't took me long, so I advise you to do this on your own. It really didn't took me long to find this, and this app is being distributed. This key is static. It's for all the users of that app. Their information is being encrypted with this key. So that's not good, because if you find a dump or you can find the encrypted information of that app, you can publicly download the app and you know what the encryption key is. So that's a problem. And obviously, I did a responsible disclosure. But then, at the end, I still like to show this image. It's a famous cryptography image from XKCD. I'll give you a minute to read it. So basically, what I want to say here is that you, as a developer, you can make a perfectly secure app, but it's still the user that's basically being the weak point. If he is being forced into giving his password, in this example with a wrench tool, or if he's dumb, I wouldn't say dumb, misinformed, that he uses a weak password, then it's still the user's fault because you did everything you could to use the right cryptography. So that's something that I wanted to give you at the end of this specific part. So let's see how you can attack an app dynamically. So what's the motivation behind this? An app might be protecting itself. It doesn't run on a rooted device. It uses obfuscation. It checks itself which certificate has been used. If you have recompiled it, it crashes, for example. So you need some information on runtime. Or you want to manipulate the app into triggering other code paths. Or you want to test internal APIs, but that's a really, I don't know if there's anything like an internal API, but you want to test internal parts of an SDK or other things. At point of view of a pen tester. So what are some tools that you can use? You can use hooking frameworks like LD preload. It's not a hooking framework, but it's a concept on Linux where you can basically hook into native libraries. It's also available on Android. There's a way to do that. And whenever the native library is doing a system call and you defined an LD preload where you preload your version of that system call, for example, or of that native library call, then your code gets executed. That's a Linux thing that's always available there. Then you have Frida. I think Frida is the correct, or Frida. Well, that tool there, which basically is capable of debugging an app or injecting itself into the app while it's running, and it gives you back. You can attach basically a callback interface for every function that you want to hook or that you want to manipulate or that you want to inspect the variables from, for example. Then you have Xposed. I think, who's familiar with Xposed? A lot of people, I think, yeah. It's quite popular, so Xposed, you run it on a rooted device. It allows you to write an Xposed module. And with Xposed, you can do things quite easily, like for example, change your email number, and then every app that uses the API call to get your email number gets the one that you defined in Xposed, for example. Or, I mean, be creative. You can change everything. Your status bar in Android. You can change system-defined functions. You can do a lot. And then you have emulators like the Android SDK, the Genie Motion, and for pen testing, if you want to pen test it on, or you want to have an emulator pre-installed with Xposed, you can use the Nathan emulator, which is, yeah, it's quite out-deprecated now. It uses Lollipop, but it has all the tools pre-installed. It's an emulator image. It's quite easy to set it up, and it gets you going. Now you can also debug your app. So you can use Dario 2, IDA Pro, GDB, or the Java debug bridge to basically debug and attach to that process of the app that's running that you want to attack. Or if you don't want to touch the app, you just want to see what it's sending over the wire, you can use man-in-the-middle proxies like man-in-the-middle proxy, which is a lightweight Python proxy. It lets you write Python scripts. That's really cool if you want to do repetitive tests, tasks. For example, always change the user identifier on a specific request. Then you can write your own script. Also Burp, that's well known. It's a well-known tool for proxying and changing network requests. And it has a lot of additions and options. And then you have Charles, which is another proxy, I think only on Mac. Not a big fan, don't use it. When I have to do something quick and dirty, it's man-in-the-middle proxy. When I'm doing quite an extensive pen test, it's Burp, because it keeps a file and you can change things, and it's really extensive. So a little bit more on Frida. What is it? It's a dynamic instrumentation toolkit, and you can use it to debug a live process. So it basically loads a JavaScript engine into the process of the app, and you can start hacking an app while it's running by just writing JavaScript code. And it uses the model of a server and client architecture. So your phone runs a server to which your computer connects, and the server is responsible for injecting into the app on the Android device. And your client is your PC. So a quick, I don't know, I have no idea of time. Because you had some hiccups. Okay. So this is a Python script that will run on your computer. And you basically, you get some parameters, you get a script, you open it, and you, basically the process, so this is the app name that you want to attack. You define a callback function that you're going to use, so when the server is injecting the app, attacking the Android app, and it sees a method that you want to hook on or that you want to grab, it will call this onMessage function. That's why we're making it developing it here. Then you create a session, and you basically attach to that app, because we use a proc name, the process name. And then we create a script, which will actually inject the script into the process while it's running. Then we close the file descriptor, and then we say, okay, every time the script finds the things that I'm hooking up, call the onMessage function. And then you load the script, and the script starts running. So how does the script look like? Well, this is an example. If you, for example, use the WebView clause, and you want to see whenever the load URL method is being used, you want to see which URL is being loaded. So that might be an interesting case for a pen tester, or if you're testing your own app. So what you do is you say, okay, dalvik.perform, you create the WebView clause in JavaScript. So this is the Frida API. You say overload the load URL method, and it takes a string as an argument. And then you say, when you find this, send back the parameter, so the URL. And then on the bottom you see, you just run, on your computer, you just run Python, you pass the script that I showed you earlier, the JavaScript piece of code here on this slide, and then, for example, an app that's called with the package name com.example.webview, and then it will start injecting the code, and it will start showing you which URL you're loading inside the WebView clause. So that's quite easy. And you can imagine the possibilities. For example, if you want to see what is being encrypted, you just hook on the cipher.final method, for example, and then you see what's being encrypted. Or you can use it as a logging framework, I don't know. There are a lot of things you can do with it. Then you have the Xposed Framework, which allows you to do the same things. It allows you to hook methods, but it's implemented in another way, because you have to write a hooking module. So you write a whole application that hooks another application. So I wrote it here as a disadvantage, because Frida, you can just set it up. You push the server to your phone or to your emulator, and you connect to it. Here you really have to make an APK. You have to use the Xposed API, and then you can hook into another APK that's on the device. And the reason why this works is you have to run it on a rooted device, and then the Xposed Framework will inject this bridge. It calls it the Xposed bridge. And it will inject it across applications, and that's how you can basically hook other applications. So when the application starts, Xposed will, in memory, see where the method is calling to, and it will replace it with your own code. So every time the method is called, it will execute your code, and it goes back to the original application. To do exactly the same thing as I showed you on Frida. So you have your com.example WebView, and you say, find and hook me the method in WebView, which is called load URL and takes a string as an argument. And you define a new method hook, so you're starting to hook this method. And then Xposed allows you to implement a before method and an after method. And in the before method, we just dump the URL, we dump it in a log. And then after, we didn't implement anything here. And this basically does exactly the same thing as I showed you with Frida, but you have to make an APK. But this might be easier because you already know how to code Java, for example, and setting Frida up is more difficult. Also, Frida doesn't work on the new versions of Android, especially not O. I expect it to not work there because they did a lot of security enhancements on the native space, but that's a little bit out of the scope of this presentation. Okay, still 10 minutes. Yeah, going to do this slide. So, so now we're basically attacking an app on network level. So we're going to man in the middle of the app, and before we do that, just a quick introduction on how SSL works. I don't know, maybe some people know this, maybe some people don't know it, so I put it in there, just a quick introduction. So what's an SSL certificate? It's basically a cryptographically secured piece of information. So just think of it like an ID card of a server that says, okay, I'm this server, I'm google.com, and if you verify that credential, then you know, because it's cryptographically signed, that it's google.com. Certificates are issued by CAs, so certificate authorities, and that's a typo there. And your Android device basically trusts a root set of CAs. So what it does, it gets a certificate, so the SSL validation, it basically gets a certificate from the server, and it sees which other certificate authority has issued this. And then it checks, okay, I have a CA that issued the certificate. Is it one that I trust? And if you trust this, then the SSL connection is set up, everything is being encrypted, and you have a secure tunnel. Now, what is the problem? A man-in-the-middle attack. So if a man-in-the-middle, through malware, through a malicious user had physical access to your device, he can somehow install its own trusted certificate on your device, then he can basically man-in-the-middle your whole app. And this is a big issue for financial applications because they have strict regulations. And the problem here is that your application, it starts communicating that it wants to connect with a server and it gets back a certificate, but it's from the man in the middle. But because we have installed its certificate, it will trust that connection. And that man in the middle will, in his turn, connect with the server and just relay that information. But in the meanwhile, he can decrypt it, read it, change it, and basically monitor everything that the app does. And that's what I use when I want to see what comes out of an app. A little bit, why would you use it? Because it lets you test, discover, and fuzz APIs, basically. And you can do it by installing a trusted user certificate, but it doesn't work on Android 6.0 and over, so you have to install a trusted system certificate, where you basically, on a rooted device, you can install your own system certificates, and you have to do that on 6.0 and over. Or just use a root exploit. You can also do that. And then it's easy to man in the middle. So here you use an emulator and you just pass the HTTP proxy flag I set up my proxy on my local host. And then I use man in the middle proxy to listen on that port on my local host. And then what you see from an app is this. So you see all the requests going in. You see posts, you see gets. You can go into the response body. You can see everything, manipulate everything. Now it's just a pass-through in this example, but you can change everything. You can write your own scripts even. And I had to do some things away because when I made the slide, it was still not disclosed. So, and it basically lets you alter everything you want. Now that I talked about attacking apps statically, dynamically, obviously I won't let you leave without having some sense of what you can do against that. So some countermeasures. First of all, you can do static protection. You can use obfuscators. You can use packers. So obfuscators like ProGuard. Who has used ProGuard? Okay, cool. Familiar with the commercial DexGuard sibling? Okay, cool, yeah. So obfuscators basically work on your code and they keep it equivalent, so it will do exactly the same, but it will make it harder for a reverse engineer to look at it, or a hacker. And what it does is it changes class names and it changes method names to something that's unreadable. So if you ever decompile a ProGuard app, you'll see that class names are changed to A, B, C instead of main activity, for example, or instead of string URL, you see string A, and then that A is passed to where it needs to be. And then you have packers, which basically, so Android is Java source code, so you can write Java source code, and you also have the capability to dynamically load classes. So what these packers do is, if you use a packer, it will grab your dex code, so that classes.dex file that I said, it will encrypt it, and it will write a little piece of code that will decrypt that classes.dex file, and it will load it dynamically. So what that means is when you look at an app and you reverse engineer it and you disassemble it, then you'll see an encrypted classes.dex file. So the classes.dex file will the code will only be available in memory while the app is running. So that's quite a good protection, but then again, as a hacker, you can dump the memory to get to the code, but it's quite, it puts the bar higher for hackers to basically look at the code. And you can also protect your app while it's running. So for example, you can use root detection to basically say, okay, I don't want to run on a rooted device because for a financial app, that's not feasible to do because you're not sure that cryptography is happening in a secure way or that all security measures of the device or of the Android operating system are running successfully, because on a rooted device, whether you like it or not, certain security measures are not being enforced anymore or not that secure as on an unrooted device. For example, you can prevent your app from running an emulator. Maybe there's no good reason why your app should run on an emulator once it is in production. Then you can write code to detect that. So how can you detect an emulator? For example, you can see the easy stuff that you can easily bypass, but that'll already give you a first layer is like looking at I think the build information from the build class. It gives away some things. But you can also look at the native libraries that are being loaded in your memory space, because an emulator uses quite distinctive native libraries. So if they are present, then you know that you're running on an emulator. You can use, for example, integrity checkers, because at runtime when you build the app, you know which certificate you have used and which certificates you have used. And while the app is running, you can see, okay, which certificate has been used to sign this app that's now running. And if it changes, if it's different than the certificate you have used while building, then you know that somebody has decompiled the app and has re-signed it, because obviously you have to re-sign the app when you decompile it and change something. And then you can also do SSL pinning. And that's basically a protection against this man-in-the-middle attack, because the problem here is that that Android app by default trusts all the certificates that are installed in on the device. But you as a developer might say, okay, my app only connects with those backends. I know those certificates, so I don't trust all the CAs on all the root certificates, all the certificates on the device. So what happens here is that you put code in your application that basically pins, SSL pinning, that's what's in the name. It pins on a certificate that you define as a developer. And that means that if this man-in-the-middle certificate is being shown, then your application knows, okay, no, that's not the certificate that I'm used to because I'm programmed to use another certificate. And then you can let the connection fail and say, okay, you don't have a network connection, for example. And that protects your app because you as an app developer, you choose which certificates that your app uses. Yeah, I'm almost done, I think. Yeah, I'm done. That was my last slide. I don't have a thank you slide, so thank you for my presentation.